something himself, something with Dvorak, who just left, right? And please take it away.
Okay, so thank you for introduction and you for coming. I will be speaking about precoloring vertices in triangle 3 planar graphs. Okay? So, coloring talk will start with 4-color theorem. So what 4-color theorem is saying is that if you have a planar graph, a graph that you can draw in the plane without crossings, you can assign 4 colors to its vertices such that no two adjacent vertices have the same color. 4-color theorem. First motivation for graph theory in the first class. Right? So suppose that you would like to have a little bit more. Right? So suppose that you would like to have a graph, G, planar, and not only that you want to find its 4-coloring, but you also want to say this vertex is red and this vertex maybe is yellow. Right? It has color 1, color 2. Is it possible to extend the coloring, or is it possible to find coloring that this one has color 1 and this one has color 2? It's like a question of precoloring, right? Color this one and then ask you to finish. So it turns out this is not possible, and it's not possible in a very bad sense. So I'll give examples. Suppose I have a graph that looks like this. So, and okay, I'll draw it such that it looks plain, and I'll try to color this vertex with color 1. So the neighbors cannot have color 1, so they have to have colors 2, 3, and 4. They are all adjacent to each other. It's triangle, right? So they have to have colors 2, 3, 4. So what is color of this vertex? It has to be 1. And now this has to be 2, 3, 4 again, up to permutation of colors. And this must be 1. Right? So if you start with color 1 here, you force color 1 here. So if I create precoloring, coloring that I color this one with 1 and this one with 2, you will never extend this precoloring to the coloring of the whole graph. So if I try to fix color of just 2 vertices, and the 2 vertices, they can be arbitrarily far from each other in the graph, you have no chance of finishing the coloring if you want to do it over all graphs and all choices of the vertices.
I'm a little confused though, because I don't see how that example extends as a planar graph.
Oh.
Or do you nest them? Do you nest the?
Yeah.
Oh, I see. I see.
And now you can.
Yeah. Okay. Got it. I understand.
Okay. So with 4 colors, you are really having bad luck. But if you have 5 colors, then things become much nicer. There is a theorem by Albertson, and it is saying the following, that you have a graph, planar graph, G is planar graph, and you can pick a set of vertices in the graph. S is subset of vertices of the graph, and you color these vertices and the coloring will extend if every 2 vertices in the set S are far from each other. So UV, so I have conditioned something like for every UV, the distance of U and V is at least, I think it's 4 or 5. Applies all precolorings, any precoloring. Or UV S precoloring of S extends to 5 coloring of the whole graph G. Okay? So you can pick vertices if they are far from each other. Far means 4, maybe 5. Let me check so I don't lie. I don't lie. And then any coloring will extend. Right? It's a funny name of the paper. It's called "You Can't Paint Yourself into a Corner." So this distance, at least 4, between all of them, the coloring exists. So it's much better than the 4-color theorem. And or much better, the 5-coloring is much nicer with respect to precoloring. And you can make this a little bit stronger, that you don't look only just on 5-coloring, but also on 5 choosability. So Albertson, true also for 5 choosability. So you can say not 5 coloring, but 5 choosability. And then the statement is that there exists some big D, such that if you have for every UV in set S, the distance of the 2 vertices is at least D, and any precoloring its extent. And this is Zdeněk Dvořák, Luke Post, Bojan Mohar, and me. And this D, we can show something like 50,000, which is probably not the best. Maybe you can do better. Open problem, can you do better than a few tens of thousands? Okay, and there is one more thing. Post 4 or 5 colorings, Post 2 and Thomas. If we will be lucky, Luke Post will come visit us in April. If not, he will not come visit us in April. And it is saying the following, that you have a graph G that is planar. So I'll have the graph G. And you have some set S. S subset of the vertices of G, and I would like to know when precoloring of S extends. And the theorem is saying that the precoloring of S does not extend, only if it doesn't extend to some short range around S. So you can say that there is some D, and you say if the precoloring of S extends to this distance D from S, then it will extend everywhere. Right? So if there is obstacle for the coloring, it must be near to the precolored vertices. Right? And yeah. And if precoloring of S extends to vertices in distance at least D, then coloring P extends to the whole graph G. And this is for 5 coloring. And it's not completely correct as I wrote it, because you can think that if this S is getting bigger, the D might be getting bigger. So the D is actually a function of S. So the D depends on S in the sense that the D is D log of size of S. So if you have size of S and you take the logarithm of it, that's the distance that you need. Right? If you have this distance, everything extends. Okay. So that was what happens with 4-color theorem if you try to do 5 colorings. Right? So we'll try to do not 5 colorings but 3 colorings. And the beginner's mistake didn't check the markers before. Surprise. You're lucky. So what's other theorem about coloring of planar graphs that is famous. The Great Theorem of triangle-free planar graphs. Great. The triangle-free planar graphs are three-colorable. And so if you forbid triangles, you need only three colors. And somehow the four-color theorem is too long time to prove it. You still need computer for it. The Great Theorem, it was proved in 50s, 60s. And there are short proofs of this now. And so, interesting thing about this is that it is not tied in almost any sense. If you come up with some small strengthening, you have good chance that you can strengthen the theorem. So, some of it is that you don't really need triangle free. Okay? You can have some triangles. So, Aksenov showed that works with three triangles. So it's saying if you have a planar graph and it has at most three triangles, it is still three-colorable. Right? So you can have three triangles and it will not ruin the property that the graph is three-colorable. Right? So what about four triangles? So for four triangles, the answer is what? Not always, right? Because there is the K4. Somehow has four triangles, and you need at least four colors. All the vertices are adjacent to each other. But there is a characterization, and you can describe the graphs that have four triangles and are not three-colorable. It exists. Description of planar graphs with four triangles that are not three-colorable. And this is a result of Dvořák, Kostočka, me, and Matthew. And how would you describe graphs that are not three-colorable and have four triangles? So this is graph that has four triangles and it's not three-colorable. If you add one vertex to it, it's still not three-colorable. Still not three-colorable. Right? So somehow we would like to have notion that is saying what are the smallest graphs, the smallest obstacles. Right? Somehow this vertex of degree 1, this leaf, it doesn't really play any role in deciding if the rest of the graph is three-colorable or not. It was useless for the property of being three-colorable. So there is a notion of critical graph. So say that G is K critical if you cannot color it with K minus 1 colors, but whenever you remove any vertex or edge, you can color it with K minus 1 colors. Right? So somehow I would like to have the smallest obstacle for a graph to be K minus 1 colorable. It was the smallest obstacle. G is K critical if G is not K minus 1 colorable, but for every H that is a proper subgraph of G, H is K minus 1 colorable. Few small examples. 5 cycles, for example. Right? You need 3 colors. You cannot do it with 2, but if you remove any edge or vertex, it's bipartite. So this would be 3 critical. Or one more, maybe. Oh. Let's hope I will not mess it up. This graph, you can check that it is for critical. Which means you don't color this with 3 colors, but if you remove any edge or vertex, you can color it with 3 colors. Okay? It's called Moser's spindle. It's the graph that you can draw in the plane such that every edge has unit length, and it shows that the chromatic number of the plane is at least 4. Okay. So what you would like to do is to have the list of critical graphs. Right? That's what the characterization will do. And so I will try to write for critical graphs with 4 triangles. This is one of them. Right? It has 4 triangles. So I'll give construction that describes all of them. The construction is following. We start with 4 cycle, and if we add edge here and here, it's K4. Right? So not 4 colors, or not 3 colors. Then the next one is I take 4 cycle, and inside I build this thing. Okay? And I add the edge on the outside and this edge on the inside. So let me show how this works. So if you have 2 vertices connected by edge, you better give them different color. I will try to show it's not 3 colors. Okay? So 1 and 2. So it means this has to be colored by 3. This by 3. This one is adjacent to 3, so it must be not 3. So maybe 1. And now I have 1 and 3 here, and this will be, these 2 have to be same. And you have trouble with this green edge that is there. As long as I had these 2 different, everything was false. At least in the sense what is 3 and what is not 3. And you can iterate this construction by gluing the same small gadget, the 4 cycle, this one edge inside instead of the green edge. And you can add these 2. And it goes on. So somehow you glue this piece. And this was originally discovered by Thomas and Walls. And they didn't try to find triangles in plane graphs. What they did is that if you put a cross cap here, now this graph has no faces of length 4 or 3, and it is embedded in the Klein bundle. So they show that there are infinitely many 4 critical graphs that you can embed in the Klein bundle without contractible triangles or 4 cycles. Okay. But anyway, and that's not all. Other thing is that if you have the green edge, you can replace it by this. Right, the green edge was into triangles, you destroy the 2 triangles replaced by this. And if I have coloring 1, 1, I am in trouble with edge. If I color this with 1 and 1, then these should be 2 and 3. Then it results in this being 1, and now I have 1, 1 edge. So it works like edge. It works like edge. And one more thing is that if you have vertex of degree 3, you can replace it by 6 cycle. So if this was vertex ABC, I keep the vertices, recreate a 6 cycle and fill it with 4 spaces. Do quadrangulation. Quadrangulation. So this is how you can get all of them. We spent a long time describing it, but we will use it again later. Both. Okay. And there was a conjecture of Grunbaum that he somehow was aware of this a little bit, and he was saying maybe if you have 4 triangles, or if you have planar graph where the triangles are not intersecting each other, then it is 3-color. Triangles not intersecting implies 3-color. And that's not true. You can already make examples from what I drew here. You can take twice this thing, the Havel's quasi-edge, should draw slower and nicer, and connect it like this. And you can check that you cannot 3-color this graph, because it is this K4 when I replaced each of these edges. So, if you say you don't have intersecting triangles, you cannot conclude the graph is 3-color. But what you can do, that there exists a D, big D, such that if all triangles in mutual distance at least D, then G is 3-color. I'll draw a picture for it. You have your graph, you have triangles, and you know that for every pair of them, the shortest path is at least in distance D. And then this graph is 3-color. It was conjectured by Havel in the 70s and solved by Dvořák, Král, Thomas. I think they announced it in 2009, and I think it's still under review. So,
I know the feeling.
yeah, it always looks like it's freshly done work if you have it submitted on the CD. Okay, so anyway, this is the thing, and so you know that if you have triangles that are far from each other, the graph is 3-color. So you can ask, can you precolor the triangles? Can you do a little bit more? Can you precolor them? Can you give them colors? And turns out, no, you cannot precolor them. So I'll erase a little bit here. So, no triangle precoloring. And I'll draw a picture, right, to show that you cannot precolor 2 triangles. So let's say I have this 1, 2, 3, 1, 2, 3, and I think I want to join it like this. Right? Is this, did I mess it up? No, this is
Prism.
ah, no. Okay, I want to color it like this. Right? And now it's not a good coloring. And you can notice that it's not good coloring even if I try to rotate the colors of this triangle. Okay, you can accuse me that the triangles are a little bit too close to each other. And it's not good coloring because of this rule. If you rotate it, so because of this one, and then. But what you can do is you can do this. 1, 2, 3. You put graph like this, and if you color the triangles the same, this will again not be 3 color. You cannot extend the coloring of the triangles. Okay? Somehow, this 1 and 2, this should be 3, 1 and 2, this should be 3. H3. And more general, if you have a graph that has 2 triangles, and everything else is 4-face, and the triangles are colored 1, 2, 3, 1, 2, 3, in the same, if you go clockwise around them and you both color them 1, 2, 3, this will not extend. Not color, does not extend. Okay, so yeah. Even if for just 2 triangles, there is some winding number argument. So keyword winding number. You will be ever interested about this. Okay, but what seems to be somehow problem is 4 faces. Right? 4 faces problem. Because somehow everything here are 4 faces. Right? So if you forbid 4 faces, let's say you say girth is at least 5, that forbids 4 faces, then you can get the analog of this theorem. And the S does not have to have the property that it doesn't have girth 5, right? So let's say I have S subset of vertices of G, and say that B without S has girth 5. So if there is, okay, yeah, you can have some strange things that are happening in S. If they are not in S, then and the coloring of S extends locally. By extends locally, I mean this picture. Then extends to whole G.
And here you're coloring with 3 colors.
Mm-hmm. So if you have no 4 cycles, then you have the analog of this Postel-Thomas theorem, that you can extend coloring of any ugly piece if it extends locally. Okay? So somehow the constraint about extension must be local. Okay. And
How far is local in this particular case?
Let me look if I draw this. It should be linear in S. So if you have the extension, at least some contour, I think Luke Postel can do it with this being 100. So it's not even a disastrous constant like this one. Okay, but what they were thinking is that maybe so precoloring triangles fails, right? And maybe precoloring 4 cycles also fails. Right? Even if you have no triangles, because you can look at this construction. If I precolor the outer 4 cycle and the inner 4 cycle, the coloring will not extend if I precolor them in a vicious way. Right? But what they think is that maybe the Albertson kind thing can still work. which means if you precolor just vertices, they are far from each other. The coloring will extend. So conjecture, there exists D bigger than 0, and such that if I have G planar and S is subset of the vertices of G, and for every two vertices in S, the distance of the two vertices is at least D, and G is triangle free, then any precoloring of S extends. Any precoloring of S extends. So conjecture by Dvořák-Král-Thomas. And so it looks like difficult conjecture. And they have easier conjecture. Conjecture 2 exists D bigger than 0, such that you have four face F and vertex V that are in distance at least D. The distance of four face and V is at least D. Then any precoloring of the four face and the vertex V extends. And the precoloring of F and V extends. So we have one conjecture, many vertices in the graph. The picture looks like this. All far from each other, and we want to show that any precoloring extends, and they have other conjecture showing that if you have just one four face and one vertex, then you want to show that precoloring of the one four face and one vertex extend. And, so we did what we did. We showed conjecture 2. We show conjecture 2. So that doesn't look as great that you can precolor any four face and vertex, but the conjecture 2 implies conjecture 1. Conjecture 2 implies conjecture 1. So this is true. So if you have a graph that has vertices that are far from each other and it has no triangles, any precoloring of the vertices will extend to a recoloring of the whole graph. Okay. So now I will try to say a little bit about how we prove it.
Did they know that 2 implied 1?
Yes, they proved
Okay,
it.
okay.
They proved
Oh,
that
they
2 implies 1.
Okay.
That's why they conjectured 2.
I see.
It's seemingly easier. Okay. So how do we prove it? Well, we prove something else. Okay. We characterize when coloring or precoloring of 2 four faces extend. In distance. So the picture is that you have a graph, you have four face F1, four face F2, and they are far from each other. And we can show when precolorings of F1 and F2 extent. Okay. Maybe I can say what's the solution to this, or what are the ones that. How would you describe those that don't extend? Or we'll do something like the critical graphs. Okay? So in the critical graphs, what happens is that if you remove something, the thing becomes colorable. Okay? And here we will have notion saying F1, F2 critical. And it will mean that I have the graph G and F1, F2, and there are some colorings of F1 and F2 that extend and some that do not extend. Right? And if I have H, that is a proper subgraph of G, then number of precolorings of F1 and F2 that extend increases. So I want to say that whenever I take a subgraph of the graph, I remove some vertex, I remove vertex V, then there will be some coloring of the two cycles that was not extending before but is extending now. Okay? So I am trying to say that everything that is in the graph is important because it is blocking some coloring from extending. Okay? If you think about the critical graphs, it's just generalization in some sense, right? Because if you have this as empty set, you would say there is no precoloring, no coloring, now we will have one. Okay? Okay, and so what are the list of F1 and F2 critical graphs? It's this. This is one part of them. Right? If I remove this, and say I will be precoloring the outer cycle and the inner cycle, I can precolor them such that the coloring will not extend. And I can also use this operation in them. And the other thing that is happening is this. Okay? What I can do is that if I have the triangles, 1, 2, 3, 1, 2, 3, I know that these are all 4 faces everywhere. I know this coloring doesn't extend, and I would like to say that this can be 4 faces. As I subdivide any edge of the triangle, and it creates suddenly 4 faces, and the coloring doesn't extend because it was not extending here. The same problem. Okay. So finally, a little bit of. Are there questions about the statement? What it tries to do? Okay, maybe you don't know. Okay, so the first thing that you can do is contract of 4 face. If you have a 4 face in your graph, it's not the precolored one. So big graph here is the F1 and F2. You can look what are the possible colorings of the graph. Right? So the coloring is 1, 2, 3, 2, right? And then opposite vertices of the 4 face have to be colored the same. Okay? So what you can try to do is that if you see a 4 face, you identify the opposite vertices in it into one big vertex. You can do things like this. And you can show that in at least one of them you don't create triangles. So if you have a four face, you can keep contracting the four faces. You can do it almost always, except one case. You don't really want to do it if this contraction will make F1 and F2 a little bit closer to each other. Unless the distance of F1, F2 decreases. We don't like when the distance is decreasing very much. Right? Okay. And now we can look at the graph, and it looks like this. You have one four face, and you have other four face. Right? And the graph, let's say, lives between them. And there are two cases that we will consider. Either the graph looks like this, that it is somewhat fat, or it looks like this. That there are four cycles that are separating F1 and F2. We will actually even allow triangles that separate F1 and F2. Okay? Separating. Four cycles. And triangles. If you remove the four cycles, F1 and F2 is now separated. And either you have many of them, many, or you have here very few. So we would like to have the case where we have many. So if you have few of the separating four cycles, what you can show is that the graph contains a grid. You can show that the graph contains grid like this. And it wraps around. Okay. And you cannot contract any of these four cycles, four faces, because the distance to the F is the same. And if you have this, if you manage to argue that this thing is happening, you can do contract identification like this. You can contract all these vertices at once, and this will create a new separating four cycle. And the distance decreases by one. So plus one four cycle, and minus one to distance. So if the distance is very big, you can show that you will have many separating four cycles. So suppose we have a picture like this. You have I'll draw many of them. The two four faces, F1 and F2. And now you have the many separating four cycles between them. So what now we start doing is, we forget about this thing that if you contract two opposite vertices, you may decrease the distance between the two faces. And we just start contracting all the four faces we see. With the exception that we want to preserve this separating four cycles or triangles. We want to preserve that there are these separations. Okay? And you contract everything you can. And if you cannot contract anymore, then you have some basic graphs. No contractions. Implies basic graphs. And there are 80 of them. And there are two cases. Either it has four face. If it has four face, you try to identify the opposite vertices. You cannot do that because you would be identifying the opposite vertices in this separating 4 cycles, and you can somehow characterize how the graphs look like. And no 4 phase. And here there were about 16 of them. Here the rest. And if you have no 4 phase, then we characterize them before. And what you can do somehow, the basic thing was that you have 2 4 cycles, and you take the shortest path between them, you break it into something that looks like this, and now you are precoloring outer face instead of precoloring just 2 faces. And now this graph has no 4 cycles at all, and there is some result by Rosak and Kavarabesh. It describes all of these graphs, and it's algorithmic, so you can generate them by computer. And so I hand wave that you have these 80 basic graphs. And the last thing you do, you try to put the basic graphs into chains and see where the coloring extends on. Last thing. Examine chains of basic graphs. And what you can show that if you glue after each other enough basic graphs, every coloring of the faces extends, unless you are having some quadrangulation, or you are having the thing that used to be here, the Thomas Wolff that I erased. And that's the whole outline of the proof. Okay. I just will say in one last minute one more thing that is interesting about this application, or consequence. I don't know if it's application. So if I give you a graph, how many colorings does a graph have? Right? I will give you triangle 3 planar graph and ask you how many colorings does it have. Does it have just 1 or does it have many? Right? And if we have this is triangle 3 and maximum degree is k, some constant, then we can show that the number of 3 colorings is some exponential function, c to the n, where n is the number of vertices. And if you have bounded number of degrees, what you can do, you can pick enough linearly many vertices that are in distance at least d from each other, and then every precoloring of these vertices will extend, and for every vertex you have 3 different colorings, so that is something like 3 to the n, right? The n is number of vertices you pick, and you can boil it down to some constant to the n. Constant not big, it's exponential. Okay, it's enough.
Thank you very much. We don't really have time for questions, but you can ask anyway.
I don't know, how big are these graphs, these 80?
Oh, no, they are actually very small. So there are graphs like this, for example. This is F1, F2. Right? They are very small. They are very small graphs. Okay? I don't think they will have more than 20 vertices. Okay? Small graphs. We enumerated them by computer. Also, the gluing is a little funny, because if you don't believe in computers, you will need 400 of them. If you believe in computers, you will need just 10.
Other questions? All right, let's thank Bernard.